We will be discussing the classic vehicle routing problem. We're going to use, for our examples, a set of 30 North Carolina shipments. The file, shipment NC30, is available on the schedule, so you can download that data file, a .mat file. Once you've done that, you can then load it into your workspace, and you'll see this information displayed. This data set has 30 shipments that have different beginning and end points. Some of them are shared, but not all of them. In total, there are 54 different locations, distinct locations in the data set. To make this into a classic vehicle routing problem, we're going to use the ending location of the first shipment as the depot for all of the shipments. And this will be a peddling situation. So all of the shipments are going to be loaded up at the depot and then delivered to the ending location of the shipment. So for our longitude-latitude matrix, we want to recreate it so now it has a total of 31 elements. The first row is the depot, and the remaining 30 are the shipments. The distance matrix is recalculated, so now it's a 31 by 31. And then we can start creating the shipment structure using the depot one as the beginning location for all of the shipments, and then their ending locations are just going to be the second through the end of the size of the XY matrix, which is 31. So 2 through 31 will be the indices of the ending location of all the shipments. The truck structure is going to begin and end at 1. So once it makes its final, and for a vehicle routing problem, we can't have more than one truck. So for each truck delivering one of our routes, each route is going to end at the last shipment, and then the vehicle serving that route is going to return back to the depot. And that's indicated by a 1 and a 1. So this makes it into a complete cycle. So these are the shipments that have been created. And then for this problem, this is a offline procedure. So for the offline procedure, since we have all of the shipment demand information available initially, we can use the pairwise savings approach followed by two-opt improvement, as opposed to an online procedure where we would be given the shipments while the vehicles are making deliveries. So with all of the information available, we'll be using the same set of optimizations for all our examples. So you can really just focus on what is different about each example as we add constraints to the problem. So for the first example, we're going to solve it as an unconstrained cyclic routing problem, or the classic TSP problem. And then in the second example, we'll start adding constraints to the problem. So this is in some sense similar to what we have done in the previous script. So I'm going to create a cost function handle using the route TC function, where I pass it the variable route and then the fixed information is the shipment structure, the distance matrix, and the truck structure. I'm going to create also using a function called plot shipment. That'll allow me, when I'm actually creating the routes, to actually display them in a convenient manner. So using plot shipment and creating that as a handle will allow me to conveniently display different routes as they're considered by the procedure. And this can be passed as an input argument to the savings and to the two-opt procedure. So this handle will be the last input argument passed to these procedures. Then we can calculate the pairwise savings and then do all of this as a single command. And when we do that, here's the figure, and these are the red dots are the locations for the shipments. Pressing any key to start the process, we can see the different steps. Now it's doing two-opt improvement. And it's finished at this point. And we have the actual single route because there are no constraints. If we want to add the depot, then this is the location of the depot at this point. And then finally we can call plot shipment again, and this will cause the actual route shipment information to be added the labels that were talked about previously. We could also solve this problem, and if we look at what is the total cost found for this procedure, it's 1,151. And if we want, we can use since this is a TSP procedure directly, we can just use the nearest neighbor procedure talked about earlier. And with that, before doing improvement, we have 1235, but then after improvement, we end up with 1145, which is a little bit less than the 1151. So the savings with 2-op improvement did not do as good as the nearest neighbor, which is consistent with our discussion of the TSP problem, where we also found that using the nearest neighbor procedure, where it was able to look at all of the different vertices and select the best, worked the best. The problem with the nearest neighbor technique is that it doesn't work well when we start adding constraints. So it works well for the TSP problem, but that good performance would not carry over when we start adding constraints. So for that, it's found that the savings procedure is the better of the two. So that's the only one that we'll be using for the vehicle routing problem. If we look at the MATLOG help information, there are other procedures specifically for the vehicle routing problem in addition to the TSP problem, and those have the prefix VRP, for example, crossover, exchange, insert, and then there is a VRP savings. There's a sweep and a 2-opt. All of these procedures are for the classic vehicle routing problem. So the same problem that we're doing today, we could actually use all these procedures, and some would actually give better results for this problem. The reason we're not doing that and instead focusing on just these routing procedures are that these procedures work in situations where we don't require the existence of a single depot for the vehicles to leave and return to. So these are a much more general routing problem. We get slightly better results, but this is a much more restrictive type of problem. So in some sense, the VRP problems and even the TSP that we talked about in the first routing script are really just legacy procedures that work a little bit better, but are much more limited. So in this discussion, we're not going to be talking any further about that. So for the first example of turning the TSP problem into a vehicle routing problem, we can add customer demand information as a first step, and then also truck capacity information. So the demand information is given as this Q vector for the 30 shipments, and it gives the demand in terms of total tons that need to be delivered in the shipment. There's also information about the density given in the S vector. So we can add to our shipment structure, and also for the truck structure, we can take the original truck structure, which had the beginning and end points for the truck, and add to it the weight and cube capacities that we used earlier for the freight transport. And then when that is done, we can then look at our expanded shipment structure, where now we have the demand in tons and the density in pounds per cubic foot given for the 30 different shipments. And as you can see, there's quite a range of different densities. So these are different types of products that are going to be delivered to the different customers. And all of them then have to fit onto the vehicle subject to the capacity constraints of the vehicle. And we're assuming that there's no consideration given to the order at which items can be placed onto and off of the vehicle. In some situations, that could be a constraint, and then we would have to add that constraint in addition to just the raw capacity constraint. So we're assuming that we can do the deliveries in any particular order, subject to not violating the vehicle's capacity restrictions. So we can now re-execute, and the reason we have to re-execute these handles are that we've changed the shipment structure and we've changed the truck structure. So these need to be recreated so that they can be used. We can then repeat these two steps, and then I'm going to do all of this as one block. So what has happened now is that instead of having a single route, the capacity constraint has forced two separate routes to be created. So we have a Route 1 and a Route 2. There's no notion in terms of these routing relative to what is the time required. So it could be that one vehicle could do each of these routes, having to return back to the depot to unload, and then freeing up its capacity, and then it would be available to do the other route. So if time is not a consideration, if you look at North Carolina in terms of distances, these are long enough distances that this would probably take at least a day or longer to do each of these routes. So it's likely that if time is an important factor, that you may have two vehicles working in parallel doing both of these deliveries. So in terms of assessing the performance of routing, the number of vehicles required is typically more important than the total time required. And if possible, if you can have one vehicle do both routes with maybe a slight increase in distance or time, that is usually preferable than requiring a second vehicle, which is usually much more costly. To see the details of our route, it's, one thing is to look at the visual display of the route to see the details of what is actually being delivered and where the capacity constraints come into play. It's useful to use a function in MATLAB called cell function, and what it does is it applies to a cell array, which in our case will be our route. And if we look at what the R2 is, it's a two-element cell array. So these are the routes for the two separate routes, both as two elements into the cell array. So what a cell function does is it applies to each of the elements in the cell array whatever function. So this function here is going to take the route and convert the route into the corresponding shipment indices. And those shipment indices are going to be used to index into the size of the individual shipments, and then I'm going to sum all of those up. Then I can calculate the total cube of each shipment, which is not given directly as information, so I have to calculate that using the weight and the density times 2,000 to get the cubic weight. Cubic capacity of each shipment. Then I could do a similar thing for the cube. Then when that's all done, I could then use the variable display or vDisplay function in MATLAB to display the cumulative information for both routes. So this is the distance of each route, the weight, and then the cube capacity. So in looking at that, the first route, it looks like it was limited by the cube. So the reason that the second route had to be formed is that the first route reached cube capacity. The weight capacity is much less than 25 tons, so that didn't come into play. And then for the second route, it took the remaining deliveries and didn't approach either the cube or the weight capacities. So that indicates why we had to go to a second route. The way that the route to index works, here's an example. It converts a route structure into the corresponding shipment indices. So if this was our particular route, as an example, then if we call the route to index function, it gives us just the 6 unique shipments, because the route vector includes 23 both initially when it's first picked up and then a second time when it's dropped off. So each of these indices occurs twice in the route vector. So this just gives us the 6 unique indices of the shipments, which is what we wanted to be able to look into the weight and the cube vectors to actually extract just those shipments that were in our route. There is also a function called isOrigin, and that tells it a routing structure whether or not it's the first time that the index occurs. So looking at this, you can see that the true values correspond to the first occurrence of the indices, and then the false values are the drop-off. So that's a way we can distinguish in a route whether or not it's a origin versus a route. And then if we put all of that together, we get the result of the route to index. So the route to index is just a helper function that's executing these two subroutine functions that are also part of MATLAB itself to help us deal with different routing scenarios. For example number 3, we're going to be adding, in addition to the previous capacity constraints, which are indicated as example number 2 constraints, we're also going to add a maximum route distance constraint. And that constraint is going to be that we don't want a route to exceed 600 miles. More typically, that would be a time restriction, that the vehicle can't operate more than 11 hours of travel because of hours of service requirements. But for this example, it gets a little easier to see if we make it just a distance constraint. And looking at our result previously, we can see that even before it got to the cube violation, the total distance here was greater than 600. So this is not going to be a viable solution the way it's currently indicated. So the way that we can incorporate that is first add a max distance constraint, and then if this constraint was not already somehow incorporated into the route total cost function, which the previous capacity constraints were already incorporated once we specified the shipment and the truck structure up here, essentially this route total cost function, by adding the truck weight and cube capacities and the shipment weight and density, the route total cost function was then able to make sure that routes didn't violate that capacity constraint. Well, what if initially this max distance constraint was not included? It turns out it actually is something that's already pre-included, so we have a way of adding that to the problem. But before seeing that, we can look at an example where if you needed to add it on your own as a special constraint that is maybe unique to your particular problem, the way that you can do that is by defining your own route total cost function. So if you look into my folder, I have my own route total cost function, and I'll put a link to this function on the schedule so you can download it. And what it does is it allows me to create my own function. My first input is going to be the route, and then I can add whatever other information I want. So what I'm going to do is take the handle to the route total cost function that includes other constraints, because I don't need to reinvent the wheel. I can take whatever current constraints are incorporated into the route total cost function, but then I can also add parameters that are specific to my additional constraint that I want to add as a special purpose constraint. In this case, it's going to be the maximum distance. And all I'm going to do then is use the function handle, which was passed to me, give it my route, and get the total cost. So this is, at this point, not including any of the information about violating the max distance constraint. But then I just put an if statement, and then if that total cost exceeds my maximum distance that was passed to my function, set the total cost equal to infinity. So I can, and I could replace this with any constraint. If I wanted a constraint that, if I had a way of identifying it, if the route involved a left turn, then I could, make the cost equal to infinity of any route that has a left turn. So this gives you a lot of flexibility in being able to incorporate almost any type of constraint into your routing problem. And then when you run the savings and improvement procedure, it's going to see the total cost of infinity and never make a route that violates whatever constraint you've added to the problem. So with this personalized my route total cost function, I can do just like I did previously, define that as my function handle. This is going to be the same plotting handle, and then just execute the same set of code as previously. And now I have a total of 3 routes to be able to see the detailed information of what's actually in those routes. Re-execute the same type of code, and you can see here that both the weight and the cubes are nowhere close to being violated in terms of their maximum amounts. But here the maximum distance constraint looks like that was the binding constraint that forced the creation of a third route, as we saw in the plot of the route. So this next example 4 is the same as example number 2, except that it's going to be using a built-in max total cost. This is such a common feature that it is added to the route total cost function. Actually looks for that information, and it looks for it in the trucking structure. So as long as we add the field max TC to a truck structure, then the route total cost function will automatically enforce a maximum total cost constraint. So we can add this to the truck structure, re-execute. I'm not going to do any plotting since it should give us exactly the same result. And notice it didn't even display the intermediate results. And the reason is I didn't include a last input variable. If you compare this, the last was the handle. And if you compare up here, the last element was the plotting handle in both the savings and the 2-op. So by not doing that, I don't have to see all of this intermediate result. And once you've seen it a few times and verified how it works, it speeds things up to be able to not include that information. And here we can see that we get the same results as previously. For the next example, we're not going to be building on the previous VRP 30 shipment data. Instead, to illustrate time windows, we're going to first start with the slide example of a time window where we have a total of 3 shipments that are going to be delivered from the depot, and the time information is given representing the time to travel along each segment of the route. So the first thing we're going to do is create the 4x4 time matrix information, and then we can start creation of the shipment structure by indicating the begin point, which is the depot, location 1, to 3 endpoints, 2, 3, and 4. And then we can add 3 additional fields that are needed for the shipment portion of the time windows. In this case, it's the time windows at the destination for the 3 shipments. And we indicate those by given a time for the E for the end. So that's the end of that shipment. That's at its destination. And then we give a minimum and a maximum for those ends. And they're 8, 12, 15, the 3 minimum beginning times. And then we have the 3 ending times. And then for the loading and unloading times, we have 0 for this problem. So we didn't include that into the calculation. So we have to indicate that as 0, because when it sees time windows like this, it also looks for loading and unloading time. So we've added that. And then at the trucking side, it includes the information for the depot. It includes the indices of the depot. And then it includes time windows for the vehicle itself, leaving and returning to the depot. And here we have for the window for when the vehicle can leave the depot, minimum is 6 a.m., maximum is 6 p.m. And then for returning back to the depot, the minimum time it can return is at 6 p.m. and the maximum is at midnight. So all that is added to the truck structure. And then we can look at the underlying shipment structure to be able to determine the route and see the detailed information about when the events of the route actually occur. We can utilize the route total cost function. And one of the options is to have it return a 3rd output argument. And that 3rd output argument gives us detailed information about the execution of the route. So I'm going to call route total cost, give it the route, which is 123, 123, the truck shipment, and then the time information. And with that, that's enough information for route total cost to be able to do the calculation. And like we saw in the slide, the minimum time required is 8 hours, and we have an exit flag of 1, meaning that it found a feasible route. But to see what the details are, we can display the output structure, and this gives us the underlying route, the location indices, the cost, in this case it's the travel time, and then this gives us the actual absolute clock time at which the different events occur. So if you look at the slide, you can see that in our second forward scan, which was the C or blue elements in the slide, then we left the depot at 10 a.m. and then arrived at the first customer at 11. We arrived at the second customer at 1 o'clock, 2 o'clock at the third, and then we arrived back at the depot at 4 p.m. and then waited till 6 p.m. to actually start the delivery process. And then we departed at 1800. So this then gives us the total amount of information. And then here we have a total time required. So the total travel time is given for this problem as 5 hours of total cost. In this case, it's the travel time. Our total in general includes also the waiting time. So here's where the 8 breaks down into what occurs at each segment. So with this information, you can recreate the actual details of what is actually occurring in the particular route. So with that information, then we can do a similar thing for our previous VRP30 shipment data set that we were dealing with. And with this data set, I'm going to define my define a travel time matrix, just like I did in the slide example. What I'm going to do is take my distance matrix, which is the distance in miles of the actual shipment, and assume an average 30 mile per hour travel speed. And then I'm going to add also, as was discussed in class, that in addition just to the time requiring just the actual when the vehicle is moving time, there's also positioning time at each stop for the truck or vehicle to get in position to do a pickup or delivery. And I'm going to assume a value of 5 minutes for positioning time that will be added to the actual travel time. And then for my unloading time at each of these customers, I'm going to make that proportional to the size of the shipment. So Q is the total number of tons being delivered, and I'm going to multiply that and assume that it takes me 30 minutes per ton. So Q representing the fraction of a ton then gets multiplied times 1/2 of an hour, or 30 minutes. And that'll be my unloading time that recognizes the amount being delivered. The constant is the positioning time of 5 minutes that's added to each route. So I can do all of that. For the first 15 customers, I'm going to assume that they have daytime delivery, which is any time between 7 a.m. and 5 p.m. The second set of 15 customers have evening delivery, which is any time between 1 p.m. and 11 p.m. So I can create then 2 different types of beginning and end points for the shipments, corresponding to which set of customers is being referred to. And then I can add that information to the shipment structure. The truck structure itself doesn't include any of the time window information, so there's no restrictions on the depot, when it can be, when you can leave and when you can return to the depot. So the truck just has beginning and end points and capacity constraints. This is now my expanded shipment structure, including this endpoint time delivery, since I'm doing a peddling type of routing where I have just deliveries at the customer endpoints. And then I can just execute the same code as previously to solve this problem, where the shipment and truck information is encoded into the handles and then applied to the savings and 2-opt procedure. And now, because of the time window, I have now a total of 4 routes. I can then display the detailed information about the 4 routes, given when the vehicles are actually departing the depot, when they arrive at the customer, any waiting time, and so on. So all of this is available in this output structure that allows me to reconstruct the detailed information about the particular routes. In particular, of interest in looking at the quality of the routing solution is to look under any waiting time. And if you look at it for the first route, there is 0 waiting time. The second route also 0 waiting time. Third and fourth routes. So all of these routes were able to be created, and none of them required the vehicle to actually wait for the time window. And I think the reason is, for this example, we have very wide time windows, basically the entire daylight time versus the evening time. If we had very narrow time windows of an hour or two, then it would be likely that we would have positive waiting being required. So these are very loose time window constraints relative to what you might see in practice. If you have an hour or two, we would get quite different solutions with quite a lot of different waiting times required.